Okay, hypothesis testing is the next focus for this course, and hypothesis testing lies at the root of much of the research that's done when you analyze the results. And on this little figure here, this is our friendly normal distribution, this top bar, and then there are other distributions like a t-distribution that have different shapes depending upon the sample size. And we're going to focus a lot on the t-distribution because it's quite often used in research, and you likely will use it at some point with your capstone. And ultimately, you remember that these distributions, the peaks of these distributions right here, these represent the mean value and approximate median and mode, assuming like a normal distribution. And when you've got two samples or two populations, you'll actually have maybe two different distributions, and they may overlap. And this compares the likelihood in which that they're similar or different in terms of their averages. For more information on this, to read the stat book, page 182 all the way to 199 covers a lot as it relates to this. And the basics, generally speaking, small samples, ones where you have less than 30 observations, tend to use the t-test, and their purpose is to determine if there's a difference in the mean values of two distributions. So if you have a normal distribution, you can focus on the averages. So you can compare maybe your sample versus a known population, or your sample versus another sample. So two different populations. Ideally, both will be normally distributed in order to meet the assumption of the t-test. Large samples, samples where you might have more than 30, they are able to use the z-test, assuming a normal distribution, although the z-distribution requires you to know a little bit more information about what you're comparing your sample against. It'll make more sense here in a second. So there are two sample t-tests and one sample z and t-test. And these are used when you know or already have a mean value already known to which you want to compare. So this is going to make a little more sense once we do an example. And you would use the data from your sample, and then you enter in the mean value, and you should know the standard deviation of the mean value of the known. So you have to have something to compare against if you're doing a one sample z-test or t-test. And then for an example, you might have a column of data for average income for your participants. I'm going to just back out and go to Stata real quick. So data editor. I created some fake data called sample income. You might have done a study on 30 people about their dietary habits, and you may be thinking that maybe income's related to it. People with more money can eat better food. So you've got data on income, and somebody might say, well, how do you know your population is representative of Kentucky? You may have surveyed people, and how do you know your population is representative of Kentucky? So you may want to compare your income data against maybe the Census Bureau's estimates, or you can have the statewide average household income, which we could get from Stata, from our county health facts, which I'll go to real quick. So you can, I coded all the counties in the United States as Kentucky or not Kentucky, sorted them, and then did by Kentucky sum household income. So Kentucky equals 0. Those are not Kentucky. Kentucky equals 1. This is Kentucky. So here's the mean for Kentucky. $41,152 is the average income for the average household, or the median household in each county in Kentucky. And there's the standard deviation. So you have this information. It's known for all of Kentucky. This is the known. Now, you want to compare your population versus this mean and standard deviation. So we can go back to the PowerPoint. So how do you do that in Stata? It's very simple. So we've got our data entered in the Stata. We want to see if the income levels are representative of Kentucky. It's very simple. So we take our sample. You can look at the sample income. You can see that we have, I hit the summary command, sum sample income, and ask for more detail. The median for our sample was 38,950. The average, or the mean, was 40,474. Now, 40,474, the standard deviation of 15,000 was our sample. And then Kentucky's is 41,152 with a standard deviation of $9,977. So our value is lower, but not by much. And the question is are our data for our 30 significantly different than the statewide average? So this has to already be known to do a one sample test. So we can do a z-test or a t-test. So in Stata, you would go up to Statistics, click on Summary, Tables, and Test, go down to Classical Test of Hypotheses, and then Z-Test Calculator, since it's a one-sided test, or not one-sided test, but a single test. When you do that, it will ask you, is this one sample or two sample? We tell it it's one sample. We tell it how many people we had, which was 30. We type in the sample mean. We type this in manually for our sample. Then we have to type in the population standard deviation. So the population standard deviation, that's not the sample. That's all of Kentucky. That's what we're comparing against. And then the hypothesized mean. So what do we think our sample is compared against? We're comparing against all of Kentucky. So that's the hypothesized mean. And then we tell it OK, and it'll give us this output. So this is a one sample z-test. So it's comparing our 30 observations versus Kentucky. So we had 40,474 for our mean with that standard deviation, and it's comparing against all of Kentucky. And what did it say for the sample? It gives us actually 3 different hypotheses. It gives us the outcome of 3 different possible hypotheses. The first one here is it's asking, is our sample less than the population mean? So do we have reason to believe that our sample is significantly lower than 41,152? And the p-value is 0.35. So there's no statistically significant difference. Next, this middle one. Is there any significant difference, higher or lower? The p-value is 0.7097. This sample is not significantly different either. And then the last one is asking, is our mean value of 41,000, or our mean value of 40,474 greater than 41,152? And again, p-value is 0.64. There's no statistically significant difference. So since the p-value is 0.64, in this case greater than 0.05, the sample is not significantly more. This is called a one-tailed test because it's only comparing if it's greater than 97.5% of the data. This one is less than 97.5% of the data. So when you're comparing for things that are greater than or less than, the p-value to reject when alpha is set at 0.05 is 0.025. However, when you're comparing if they're equal or not, are they equal or not equal, is there a difference higher or lower, then the p-value is 0.05. So when you're comparing if something's less than or greater than, the p-value is 0.025 traditionally. when you're comparing if it's just not the same, if it's significantly different or not, the p-value is 0.05. So now are your data different using the t-test? So you can also do a t-test, and the t-test is just like the z-test. So we want to see how it performs. So we go through the same thing: summary, stables test, classical test of hypotheses, and then instead of z-test calculator, we can click on t-test calculator right there. T-test calculator, the one below the blue. It will prompt you for this information, but notice now everything is about the sample: sample size, sample mean, sample standard deviation, and then only here do we put in the number for the population that we want to compare it against. So sample mean was our 30 samples versus all of the Kentucky numbers. So we don't need the sample, we don't need the population standard deviation. Now we just need the sample standard deviation. So we could get that from our summary stats, and we tell it to go, and then we get these same p-values. Now, the 0.4037, it's obviously greater than 0.025, so there's no statistically significant difference that says that our data are somehow less than 41,000. This middle one is 0.80, so again, no significant difference since it's greater than 0.05. And then the one that's down here saying that our mean from our sample is greater than the Kentucky value for income, and again, no evidence that ours is significantly higher, so the p-value is 0.596, which is greater than 0.025. So no statistically significant difference from the t-test either. So those are the results there that I just communicated. So again, notice there's a symbol for less than on this one, and the p to reject is 0.025. Here there's an equal sign. It's equal or not equal, and the p-value is 0.05. And then here, this is a one-tailed test as well, the greater than sign. So the p-value to reject is less than 0.025. Since 0.5963 is greater than 0.025, we can't say there's a statistically significant difference. So that concludes the first set. The next part is we're going to be comparing two samples, or comparing two sets of results that you might collect from a study. So that will be the next one.